Hello. In the last lesson, we discussed Rutherford model of the atom, and we found that there are some problems with it. Well, this is the way models in science actually develop. When we try to explain something, it should account for observed phenomenon. Well, we have a lot of observed phenomena that can be used to explain the models of the atom. Now, what are some of the common phenomena that we should be looking at when we talk about atoms? Well, let me show you one simple example. A scientist named Bohr, I'm sure most of you must have heard about Niels Bohr. Now, Niels Bohr was familiar with the emission spectrum of hydrogen. Now, what is the emission spectrum of hydrogen? Here I have in my hand a hydrogen source. In fact, the light you see is actually emitted by hydrogen. Now, what happens to it when this light is passed through a prism or something that can actually split this light? Let me see if I can show that to you. Well, this is the normal hydrogen source, and I'm going to pass the light emitted by hydrogen through what is called a grating and see what you get on the screen. Watch that carefully. Now, you get what kind of colors? Look at the colors carefully. You get blue, green, yellow, red, and all these kind of colors. Now, any model of the atom that we propose or anybody else propose must explain this observed phenomenon. How is it possible that light emitted by hydrogen is made up of these colors? Well, that is what Bohr attempted to do. Let's look at what Bohr said. Bohr observed that when light produced by a hydrogen source is passed through a prism, it splits into discrete colors that you can pick one color from the other. In my demonstration, I used a grating. Well, in the case of the prism, it will look like this. Now, each color in the spectrum corresponds to a particular energy of radiation. This is where Bohr actually nailed the atom model. He said each color must correspond to a particular energy. That means the structure of the atom must explain that particular energy for each color. Now, this is actually what you saw in the demonstration. Now, since these radiations come from atoms of hydrogen, Bohr argued that an atom can only emit radiations of a certain frequency. That means an atom cannot radiate all kinds of frequencies at the same time. It can only emit discrete frequencies. Certain frequency, and then the next one is certain other values. There is nothing in between. So whatever model of the atom we subscribe, it must be able to explain these discrete energy values of the radiations. Well, so what did Bohr do? So Bohr connected this idea to the model of the atom that he proposed, and he came up with 4 postulates. These are important postulates, and let's take a look at each of these postulates. Postulate number 1, he said electrons assume only certain orbits around the nucleus. It cannot assume any orbit. It can only assume certain orbits around the nucleus, and these orbits are stable and are called allowed orbits. Now, what is the problem we discussed in connection with Rutherford model? According to Rutherford model, an electron moving around the nucleus must to radiate energy, and therefore it must lose energy and ultimately fall into the nucleus. Now Bohr said, well, although there's a theory which says that at these allowed orbits no radiation do take place. In other words, these orbits are stable. You see, there are very many physical theories which defy explanations. In fact, the boldness of scientists to come forward with such postulates which can be experimentally tested is the core of many of these scientific principles. This is one such thing. Bohr said there are certain allowed orbits around the nucleus where electrons will not radiate energy, and therefore those orbits are stable. In other words, here is an allowed orbit, another allowed orbit, an orbit in between is not allowed. There cannot be any orbit in between. So only certain orbits are allowed. Each orbit has an energy associated with it. For example, the orbit closest to the nucleus has an energy E1, and the energy of the next orbit is E2, and so on. In other words, we can assign each orbit an energy value, and that is the core of Bohr's model of the atom. The third postulate that Bohr came forward with is light is emitted when an electron jumps from a higher orbit to a lower orbit, and absorbed when it jumps from a lower orbit to a higher orbit. Now, where is the energy of the electron more? Is it in the inner orbit or in the outer orbit? You know, in mechanics we talked about the potential energy. The potential energy is greater as the distance between the objects increases. Is that right? And therefore, the energy of the inner orbit, E1, is less than the energy of association with the second orbit, is less than the energy associated with the third orbit, and so on. So light is emitted when an electron jumps from a higher orbit. If an electron from orbit 2 jumps to orbit 1, now in order to be in orbit 2, an electron has to have a certain amount of energy, and if that electron is going to stay in orbit 1, its energy has to be less. So if an electron jumps from this orbit to here, it has to throw away the extra energy. And this thrown away energy is what you see as light. Light is emitted when an electron jumps from a higher orbit to a lower orbit, and is absorbed when it jumps from a lower to a higher. If an electron has to move from the first orbit to the second, it has to absorb some energy from some external source. And when an electron moves from the second orbit to the first, it throws away that extra energy. And you can see how this principle is so well suited to explain Bohr model of the atom. And the fourth postulate, the energy and frequency of light emitted or absorbed is given by the difference between the two orbit energies. In other words, when there is an electron transition taking place from one orbit to the other, the extra energy is radiated, and the frequency of radiation, each radiation has a certain frequency, and that frequency depends on that energy difference. Well, we will talk about that as we move on. Now, Bohr argued that the angular momentum of the electron in an orbit is quantized. What's the meaning of that? The angular momentum is quantized. It means that the angular momentum of the electron can only have certain values. That's the meaning of quantization. Now, according to Bohr, he said the angular momentum of electrons can only have values that are multiples of h over 2 pi. Now, this is a very important constant. What is h? H is actually Planck's constant. Well, the idea of quantization was actually first introduced by Planck. Now, Planck's constant, let me see if I can give you the value of Planck's constant. Planck's constant is an important constant in nature, and it has the value h equal to 6.64 times 10 to the negative 4 meter squared kilogram per second. We will be using this very often. Now, once we are familiar with this h, we will be able to write expression for the energy difference between the two levels. For example, let me see if I can write that again. An electron moving from level 2 to level 1 will emit an energy that is given by E2 minus E1. And we can write this using H as E2 minus E1 equal to H times F. Now, this is an important relation. This is a quantum of energy. The difference between any two levels is Planck's constant multiplied by the frequency of radiation. That means you have a greater difference in the energy, you get a greater frequency of radiation. Now, you know about electromagnetic radiation. Red is low frequency, violet is very high frequency. So in order to get a violet color radiation, the difference in the energy must be much greater than when you obtain a red radiation. We will be looking at these as we move on. So according to Bohr, the energy of an electron is quantized. The angular momentum of an electron is quantized, and it can only have values that are multiples of h over 2 pi. For an electron in orbit, the centripetal force to keep the electron in orbit is actually provided by the electrostatic force between the electron and the proton. Now, let me say one thing here. The model of the atom that Bohr developed is using specifically hydrogen atom. Now, hydrogen atom has one proton in the nucleus and one electron. So, Bohr model of the atom is specifically for the hydrogen atom. Later on we will see Bohr model actually breaks down when it comes to higher atoms. So, when you have one proton in the nucleus and one electron in an orbit around it, what is the electrostatic force between them? Each has a charge E, is that right? So that will be Q1, Q2 divided by R squared, where R is the radius of the orbit. So the centripetal force is actually provided by the electrostatic force between the proton and the electron. And we can write this relation. mv squared over r, which is the centripetal force, equal to k, the constant of Coulomb's law, q1, q2, q1 equal to q2 equal to e, and r is the radius of the orbit. Now, the angular momentum of the electron in orbit is m times v times r. Now, how many of you recall that from the first part of physics we did in the last semester? The angular momentum of an object of mass m moving with a velocity v at a distance r from the axis of rotation is m times v times r. We're going to use that over here. And according to Bohr, that angular momentum is quantized. The angular momentum has to be some multiple of h over 2 pi. and we have now used n as a multiple, where n can have the